Okay, welcome back, everyone. So today we'll finish our discussion of a review of linear algebra. And we're almost done, but what we're going to do today is we're going to apply some of these ideas regarding matrix multiplication. And the key thing to remember about matrix multiplication is that when you multiply two matrices, like in this example, to get a certain row and column, you essentially multiply all the entries in that row of the first matrix with that column of the second matrix and sum them together. So you get this times this plus this times this gives you this. And that idea, we said, also holds true even if the things inside those matrices are themselves matrices or vectors. It still works the same way. Okay, and that basic operation is something I want you guys to be very good at so that when we're going through machine learning material and there's equations like this on the slides, you don't have to stop and decipher what's going on, that it's kind of automatic. You understand, oh yeah, this is what's happening, and so you can understand the higher level machine learning ideas. So as an example of some of this stuff, let's take a look at this short problem, which requires putting together a few of these concepts. So here what we have is we have a matrix B whose entries are Bij. So I denotes the row, J the column. And then we have a matrix C. Entries are Cik. And what we're interested in doing is writing this particular sum in terms of not the entries, little c, little b, but in terms of those matrices themselves. So in some sense, we have to, you could say, work backwards from the typical way. When you think of matrix multiplication, you think of multiplying matrices that has some effect on the entries. Here we're saying we have a desired result in terms of the entries. How do we figure out the matrix operation? And this is something we will do a lot over the course of the semester. So does anybody have any ideas of how we might approach this, just at a high level?
Matrix multiplication.
Sorry?
Matrix multiplication.
Yes, this is all about matrix multiplication. The question is, how do we start? How do we apply matrix multiplication here? So when we look at this expression, when we multiply two matrices, we said that the inner dimension of the matrix multiplication is the one where we have this multiplication and summing, right? So what is going to be the inner dimension in this expression of the matrix multiply? I, exactly. Because I is the one we're summing over. So if we want to write this in terms of matrix multiplication, we have to use two matrices whose inner dimensions in the product both are I. And so, for example, if you start by saying, well, let's just take a guess. What if I multiply C times B? With the way this is defined, you can see that C has I going down this way and K going down this way, and B has I going down this way and J going down this way. And you can see that doesn't work because we have K and I. There's a mismatch in those indexing variables. Okay, so what can I do to fix this? We can transpose, exactly. Okay, so there's actually two ways to do this. So let's start with the first way. Let's see what happens if we have the matrix C transpose. And I really suggest drawing pictures of this stuff. I even do this, even though I know this stuff quite well. If I'm just trying to visualize a problem, see what's going on, I'll draw some pictures. And so because we've transposed C, what does that do to the two indices? It flips them, exactly. So this C transpose now has I going across the columns and K going down the rows. B we have not changed, so that is I going down the rows and j across the columns. And now we're summing over I, so let's give this thing a name. We'll call this A, matrix A. And so in the matrix we're creating, what is going to be the row index? What variable do we use for the row? K, right? It has to match the expression on the left where we used K for the rows. Now the columns are going to use J because that has to match the other side of the equation. Okay, so I would say we're halfway there because what we've done is we've realized that this is related to this matrix multiplication. But there's still one key difference. In this equation, we have full matrices. This is, what's the dimensionality of this constant, or what's the dimensionality of this quantity? It's a scalar, right? So this is a matrix, this is a scalar. So we're not quite done. The last step is to say, I need to extract a certain element from this matrix, and then that will give me this scalar, right? So which element do I extract from this matrix to give me this scalar? It's just the kth row and the jth column, okay? So, so one way we could write all this then would be the sum we're interested in computing, which is the sum over I, Cik, Bij, is equal to, now we can, so in this class, I use this little triangle above the equality to denote a definition. So definition is just something like I'm just defining A this way. It's not something you can argue about. You can't say, no, A doesn't equal that. I'm saying, no, that's the definition. So we've defined A to mean this. And now that we have that definition of A, we can apply it. So over here, we can say, oh, that is going to be the A matrix looking at the kth row and jth column. And finally, one last step is we want to write everything in terms of B and C matrices. So what's the last step now? Because so far, this is not in terms of the B and C matrices. This is not in terms of the B and C matrices. I need the final expression to be in terms of B and C matrices. So what do I write? C transpose B, exactly. Okay, so this is the final answer to the problem here. And if you go backwards, you know, from here to here, this is pretty much that equation that I presented when we first started talking about matrix multiplication. So what we're doing here is we're sort of going backwards or reconstructing. But it's important to be able to go both ways. Yes?
On the notes on GitHub, there's an extra summation over K on the outside of the original summation. Do you mind going over that?
I think you might be looking at the wrong page.
Oh,
I did the same thing.
Yeah, we're going to continue this on the next page, but so far we don't have that sum yet. Okay, was there another question in the front? No. Okay, great. So is everybody good with what we just did? Okay. Does anybody see another way we could have, another approach we could have gotten to get a different but equally correct answer? That's right. We can swap the order of B and C. So let's first ask, why can we do that? So if we look at this expression up here, maybe I'll write, I'll erase this because this was not really useful. But okay, so this guy, because we have scalar quantities, we know that scalar multiplication commutes. So I could also write this by swapping the B and the C. And that might give me the idea to do the same thing we did, but now transpose the B to move in its index I so that it's the inner one. And if we do that, we get B transpose C. And drawing the picture again, we have, in that case, J coming down the rows and I across the columns. And then for C, I goes down the rows, K across the columns. And now I'm going to once again define this as A, which like kills my previous definition. It's a new definition. For this A, though, notice what is the index coming down the rows now? J, exactly. So that's a little different than what we had above. And so, so this new quantity, which we could write either the same as above or the other way, is going to be matrix A. But now I'm looking at the jth row and kth column. And finally, I'm going to plug in my expression, which is going to be B transpose C, looking at the jth row and kth column. Okay, any questions here? And now that we have these two answers, we should do a sanity check and see if, in fact, they agree with each other. So what do we remember about transposition? If I transpose this matrix multiply, what do we get?
B transpose C.
B transpose C, exactly. So, so that means that if I transpose that product, that's the same thing as swapping its indices. And here we have the transposition of the matrix, and we also get the swapping of the indices, so everything checks out. Everything is as we expect. And in fact, you could have gotten that second answer directly by doing this the first time and then just say, oh, well, I know this is true, so just go directly to this. That's fine too. Okay, great. Is this making sense? All right, something you think you could do on an exam or a quiz or homework? Okay, great. You'll have some practice of this type of stuff. Let's move on to a slightly more complicated version of this. So here we actually have the same quantity from the previous page, but this is a scalar. So now we're going to square that scalar. And let me ask you another question. Is this quantity, the thing I'm squaring, is that a function of some variable I? What do you think? How many people think it's a function of I? Good, no one. Because I is a dummy variable, and once you do that summation, there's no more i's. Right? Another way to see this is if I write something like I going from 1 to 3 of some variable ai, I can write it with a sum, but I can also just write it as a1 plus a2 plus a3. So you can see here, there's no dependence on some quantity I. It's just the sum of those three numbers. Here I is a temporary variable, a dummy variable that we're using to express this idea. Okay, so coming back to here, you guys correctly realize that this is not a function of I. What is it a function of? What variables is it a function of? K and J, exactly. And what happens when we take that and we sum over K? Then it's a function of what? J alone, right? So that's always something to keep in mind, is when you're doing these things, like what should this final thing depend on? What disappears, what remains? Okay, so let's say we use our result from the previous page. We know that this thing is the C matrix transpose times the B matrix, and then I'm going to extract K and J. This is from previous page. Okay, so that means that the quantity we're interested in it's the sum over k on the outside. Sum over k times sum over I times Cik Bij quantity squared. We can write this using this idea above as C transpose B Kj squared. Sure, we can do that, but not sure how to simplify that. It's a little bit messy. Remember, our goal is to get rid of that sum over k. So another thing we could do is instead of squaring it, let's write that quantity twice. C transpose B, again, Kj. And now, when you step back and look at that, this has the same structure as what we did on the previous page. There's some matrix here. We know it's a matrix because it has two indices. And there's another matrix here with two indices, and I'm doing some kind of matrix multiplication. So now it's just a matter of sort of massaging things so that it's clear exactly what matrix multiplication is occurring. So who sees a way of doing this?
Transpose of the first.
Exactly. If we transpose the first one, then we can make k the inner dimension, which is what we want because we're summing over k. So to transpose the first one, we have B transpose C, and then we swap these. And then we have C transpose B, Kj. And now, we can recognize this as a matrix multiply. Does anybody see how we express that as a matrix multiply? Like, how do we get rid of the sum k? So what variable will remain after we get rid of the sum k? Just the j, right? So we're looking for an expression that involves j but not k. It has no more sum. Any ideas? Yeah.
It's just B transpose C, C transpose B, J by J.
Exactly. So we have, B transpose C times C transpose B. That's the matrix, but now we're going to extract one element because the quantity we're dealing with is just a scalar. We're extracting the jth row and the jth column. In other words, the jth diagonal entry. And that's the final answer. We have expressed this quantity here using B and C without any sums. Okay. One of the big reasons that this matters for machine learning is, I guess there's two reasons. So number one, from just an interpretability, it's difficult to interpret equations or expressions where you have a lot of different sums in them. You have to stare very hard at what is being summed over, how it's being summed over. It's just hard to wrap your mind around what's happening. If you can express things in matrices, it just makes things a lot more clean and elegant. The second thing is, when it comes to implementing this stuff in software or in hardware, or when you think about programming it, you can always program a sum using a for loop. So you could program this expression with two for loops. The problem, though, is that most compilers are not smart enough to turn that into efficient code. But instead, when you program this using matrix expression, then the compiler says, oh, you have matrix multiplies? I know how to do that really fast on this hardware, whether it's a CPU or a GPU or whatever. It goes into a much more efficient mode of operation, and it executes this way faster than it would execute your for loops. Maybe like a factor of 10 for every for loop. So this might be 100 times faster than this. Yeah, so those are the motivations for dealing with linear algebra. instead of leaving everything in terms of summations. Okay, great. Any questions remaining? Okay, then that covers our linear algebra review. So you have homework to practice this. I would suggest doing the homework first. Once you feel like you've mastered it, then take the quiz. It's kind of like a check. It's like, how well do you know this stuff? You have 5 chances to take the quiz. Doesn't count for anything except practice. And then next Friday, we'll have an exam. It'll only be half the period, so 25 minutes, where it will be similar to the homework in style. You'll have some problems. You just need to go through and do some derivations, kind of like this, maybe. Some of them might be like this page. Okay. Any questions? Okay, great. So just one last page for this unit. In terms of the coding, because I will lecture about coding a little bit, though not very much, but I'll just point a few things out in the lectures. So the main points here is that if you're doing Python, if you're working in Python and you want to do this kind of linear algebra stuff, then the main package you're talking about is NumPy. So Python is a language where you have to load in all these different packages to give you the abilities you want. And NumPy is the main numerical computing package. A few advanced linear algebra functions are not included there. You could find them in the SciPy library, but not really very many. For us, I think almost everything will be in NumPy. There's a couple demos that point out a few things about NumPy that I found surprising coming from MATLAB. And if you look at the main course repository, the README file there, which is what you see when you navigate to it, on the bottom it has some resource links about practice problems with Python and NumPy. And I added these just because in previous semesters I had students ask me, where can I have a bit of time now, I want to get better at this stuff, where can I find it? And so I just put a few practice links there. There may be other ones that are good too. And the first lab is pretty basic, again, just getting some experience with NumPy to do things. One of the differences between Python and MATLAB is that in MATLAB, everything is a matrix. Maybe not surprisingly, because it's matrix laboratory. Whereas in NumPy, you can have one-dimensional quantities, vectors, which are sort of like lists of numbers, you could say. Now, there's such thing as a Python list. It's a little different, but it's similar. And the idea is that if I just have a one-dimensional list, there's no such difference between a column and a row. The whole idea of a column versus a row only makes sense when you say I have a matrix. In that case, do I have like a matrix with one column or a matrix with one row? Those are different things, right? But in NumPy, when you're working with a one-dimensional quantity, it can't be a row or a column because those are two-dimensional ideas. So that's one of the things that's a little different. So you can define a two-dimensional quantity in NumPy, and that's a matrix. You can define a three-dimensional quantity. That's called a tensor. We'll talk about those later, and any dimensions. So that's the NumPy ND array, which is like the main unit of working in NumPy, the main quantity. Okay, so that's it for this unit. Any last questions on anything linear algebra, software, or hardware? Okay, great. So the next unit, we'll finally get into some machine learning, and we'll be using our linear algebra from the get-go. So a lot of these lecture slides for each unit, there'll be some kind of practical application that we're using in the demonstration code, and we're using it kind of bouncing back and forth between the theory and applying it to that problem. And so for this unit 2, lecture 2, our problem, our application is predicting the fuel efficiency in miles per gallon of a car, given features like the number of cylinders in the engine, the horsepower of the engine, the weight of the car, et cetera, et cetera. And you can find this in the demo 2, AutoMPG. This is a Jupyter notebook, so it has this IPYNB extension. The labs, especially these early labs, are very close to the demos. So if you've never seen Python before, just look at what's happening in the demo and just kind of use that as a guideline. And as you get more experience, you'll know this stuff, and the labs will become a little bit more challenging, a little bit less like the demos. But that's basically, you can just learn by example. So this particular demo, instead of providing the data in a file like in Lab 1, we'll get the data directly from a website, and we're going to be using to kind of load that data and store it. We're going to be using something called a Pandas data frame. And a Pandas data frame is used extensively in machine learning. And what it does is it gives you a convenient way to store, view, and pre-process your data. I'll show you some examples on the next page, but basically, the main object within Pandas is called a data frame. We often will name it with the variable df, and it has three main fields. It has a values field, columns, and index. The values field is the numerical data values in NumPy format. The columns field is the labels of the columns. These are like strings, and you can actually work with them directly as strings, as I'll show you. And then the index column goes down the rows. The rows are basically the elements in your data set. So if you have like a data set with 10 entries, like 10 examples, then the index would index over, maybe 0 to 9 or something like that. Now, of course, it's more complicated than that. There's other fields. There's many functions within Pandas. But let me give you an example. So just backing up a second, when we work with Python, the very first thing we do is we load in various libraries we're going to use. So we're going to import the Pandas library. We're going to import NumPy. And often we give them an abbreviation just because when you use a function from that library, you have to say, where to find that function. So everyone abbreviates Pandas to PD. Everyone abbreviates NumPy to NP. And so we can then, when we run a Pandas command, we'll do PD dot and then the command name. Okay, so here we're going to import a particular function from a particular data set, and then we're going to do this command, fetch from OpenML. This is the data set name, blah, 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 and it gives auto MPG. And basically, we're importing it directly as a Pandas data frame. So when we look at the data part of that, that thing is a data frame, and this is what it looks like. So each of these is a sample in the data set. And you can see the first sample index is 0. The last one is 397. In Python and NumPy, you always start counting at 0, not at 1 like in MATLAB. So there's 398 different examples of the data. And here is the values column. You can see directly the interpretation. This first column here tells you the number of cylinders in the engine. The second one tells you the displacement. These are all like, this is the year. So these are cars from like 1970 to 1982. So they have engines that are typical of that era, horsepower, weight, and so on. So this is all the data that we're typically, at least for this data set, using for prediction. And the thing we're trying to predict, called the target, is given in a separate field. And so here you also see 398 examples, and here are the miles per gallon for these cars, 18, 15, and so on. 44 is the highest one, at least in this summary. So this is the Pandas data frame. This is called a Pandas series. It's like a data frame, but it only has one column. So typically the thing that you're using for prediction would be this data frame, and the thing you're trying to predict might come in as a series. And that's typically how we start with the data. Within this, Pandas has a lot of
pre-processing commands, like you can ask it to look for missing data, you can tell it how to deal with missing data, you can do all kinds of different pre-processing with it. It's very friendly in that way. Okay, so any questions on anything Pandas related? Okay. The best way to learn all that stuff is just by experience, so I'm not going to go on any more than that. Now, back to the math and the terminology. So I'm going to try to be consistent throughout the entire semester and use the same variables to mean the same things all the way through. So the variable y we're always going to use as the variable we are trying to predict. And there's going to be different names for that. The names I'm going to use most often are target and label, but if you look at other books, other papers, if you talk to other people, especially statisticians, you'll find that they have different names for the same thing. So statisticians often talk about the response variable or the dependent variable. So even though we won't use these names, they are kind of important to know just because it's hard, to know what's going on talking to those people who are reading their source material if you don't speak their language. So that's what we're trying to predict. Now the thing we're using for prediction, we're going to always call that x. And we are going to call them features, but they're also called sometimes predictors, regressors, attributes, independent variables. We saw that this triangle equal means define, and here we see a bold lowercase x, which means column vector, right? So here we have things expressed as a transposed row vector. That gives us a column vector. Now the data we're working with is going to be a set of examples of x's and y's. And they come in pairs, right? So for a given vehicle, which is, let's say, this very first one in the data set, this is its miles per gallon. For the second vehicle, this is its miles per gallon. So it's important to pair them. If you if you broke the pairing, there would be nothing you could predict. You would lose all the structure. Okay, so these things come as pairs, and that's why I'm putting these round braces on them to indicate these things come together. The other thing we have here is because we have a bunch of them, we need a variable to index through them, and I'm always going to use I to index through our data set. The other thing you see here is how many examples we have, which is n. So this curly brace, I'm usually going to say that denotes a set. So we have a set of n examples, and we're indexing that set using the variable I going from 1 to n. Okay, and I'll try to be consistent. N is the number of samples throughout the quarter, number of samples in our data set. Okay, any questions so far? Okay. So as humans, we can often spot patterns pretty easily, and we can get some intuition from those patterns and maybe decide on a course of action to take. And so one of the simplest things you can do, given any two variables, you can plot them together where you plot one on the horizontal axis and one on the vertical axis, and each of those dots is now going to be one element in our data set. So this is our almost 400 elements in our data set. And now that we look at this, you can sort of notice that there is a certain relationship between horsepower and miles per gallon, right? So as horsepower goes up, miles per gallon tends to come down. Now, it's not a perfect relationship. It's not like, I can tell you for a given horsepower exactly what that miles per gallon is because there's a bit of width to this scatter plot. But you can see that I should be able to predict something. If you tell me horsepower, I can give you some reasonable guess on what the mile per gallon is going to be. Right? That's what you can learn from this. If you plotted this and you saw just a round cloud, you probably know this is maybe a hopeless problem. I don't really see how we can predict anything. Unless maybe we have some other information that is not shown in that scatter plot. Okay. All right, so any questions? Okay, so coming back to the linear algebra, we're gonna pack our data into a feature matrix, which we'll call capital X, and a target vector, which is gonna be lowercase y. So consistent with how we saw it in PANDAS, just like that PANDAS series, we're gonna have the different entries in our data set be different rows in a quantity. So since we have just a single thing we're predicting, we're gonna get a column vector here. But remember that we are using various things for prediction. We have 1, 2, 3, 4, 5, 6, 7, at least 7. Maybe we won't use them all. But those are the 7 different things we could use. And so one way we can think about it is I can think about those as individual scalar entries, or I can think of this whole thing as a vector that represents one sample worth of the things I'm using for prediction. In other words, one feature vector. This is like x1 transpose. Transpose because it is a row here. Or this is the nth one, the last one on our data set. And here is the definition of how you take those individual scalars and you pack them into a row vector. Okay, so we have like the matrix view. We can also view every entry in our data set as a vector, or we can view the target altogether for our data set as a column vector, or entry-wise as scalars. Okay, so again, n, number of samples in the data set. Oh, a new variable here is the number of features we're using. Number of features in this case could be up to 7. Okay, so that's the matrix vector representation of our data. Any questions? All right. So there's many, many ways to go about trying to predict the target using the features. What we do in this unit is we start with the simplest possible method, which is based on linear models. And that's just because we want to start simple and understand it really well. And as the semester goes on, we'll make it more complicated and things will become a little bit less understandable. But for this, you'll see we're able to understand everything. So again, as we saw, we have a scalar target variable y. We have a column vector of features x. And now, what do we mean by a linear model? So what we mean is that we can represent that scalar target y as approximately equal to some coefficient, I'll call beta 0, plus beta 1 times x1, which is the first feature, plus beta 2 times x2, and so on, all the way to beta d times xd, remembering that we have d different features we can use for prediction. Okay, so now an important thing is the use of this approximately equal. We're not saying that the target y is exactly equal to this, because in reality, our data is never that clean. It's never that perfect. There's always going to be some noise or some modeling error. And so that's why we're just saying, roughly speaking, we are pretending when we adopt this model that y is approximately equal to this linear combination. By linear, we mean that each one of our features is multiplied by some adjustable scalar parameter beta. Now we also have this offset or intercept beta naught, which is just one more adjustable parameter, which says, there could be just like an overall shift between the linear combination of x's and our y's. And technically speaking, once you have this shift in there, the model is no longer purely linear. It's something we call affine linear, which is like linear with a shift. Okay, everybody with me so far? Okay, now we do need a name for this quantity here. This is our prediction. If we figure out how to set those betas, we are going to get a prediction. We're going to call that prediction y hat. And this is a definition. I'm just going to give that a name, y hat. And so notice on one side we have an approximate equal to, and on the other side we have an equal to or a definition. Okay, so that means that our prediction, we don't expect it to be perfect. But it is our prediction. Okay, so these betas, these are the prediction coefficients. We have a total of d plus 1 of them because we have d of them that are multiplying our features, but then there's this one other offset. And if we want to be explicit about how much error we have, the difference between the true target and our prediction of the target, we can call that epsilon, y minus y hat. Prediction error, sometimes people call this the residual. What remains after you do your prediction? Okay, everybody good so far? So the key question for us now is how do we choose the best beta? All right? And this is, in some sense, a question we will spend all semester trying to answer, but for different definitions of best, different considerations of what we mean by best. We're always given the data. This is what we have in machine learning. So we're given a data set. In some sense, the data set is everything. In practice, we might also have some domain knowledge, some expert knowledge, but really the pure machine learning perspective says all you need is data and knowing how to work with data. You don't need to know anything about the data. So for example, when it comes to the final project, I'm not going to tell you anything about where the data came from. I'm just going to give you the data and say, go, do the prediction. And that's all you need. Okay, so how do we get this best beta? What we're going to do is we're going to use least squares, basically. Least squares is a heuristic approach. It's just something I'm sure you guys have all heard of, you've seen, you've done in previous classes. It's just a place to start. Later, we will understand when least squares is good, and we will be able to interpret it. But for now, it's just a starting point. So this is what we have. This is our prediction. I want to point out one other thing, is that sometimes you'll see the data sample index, I, and sometimes you won't. So notice over here, there was no sub I, right, on this Y or any of these X's. That's because we weren't talking in specific about our data. If you want to think about it this way, you could say, once I'm done processing my data and using it to learn my betas, at that point, X will be what I'm applying it to. So that's not part of my data set, so it doesn't have this I index. It's just some new piece of data, X, that I'm working with. And this is going to be the unknown thing I'm trying to predict. Okay, so that's why sometimes you don't see the I's, but now we're saying this is the prediction you get on the ith sample of your data set. So that's why it has an I there. And this is the first feature of the ith sample of your data set. So that's why it has two indices. And if you remember, when we define this feature matrix, you can see there's two indices. So I is sample index, and J is feature index. So that's what we have over here. Okay, so the ith sample prediction, y hat I, is beta 0, intercept, offset, plus beta 1 times the first feature of that data sample, plus beta 2 times the second one, and so on, all the way times beta d times the dth feature in that data sample. So we would like to express this in terms of a a vector multiply, like an inner product. So how can I express this using a vector of stuff on the left, which deals with the x's, and a vector of stuff on the right, which deals with the betas? How do I form, does anybody see, how do I form the vector of the betas? What do I put inside there? So we're trying to express this using some row vector times some column vector, and this has the betas.
1x.
Sure, yeah, we can start over here. So this would be a 1, and that makes sense if what is the first entry in the betas matrix?
Okay, that's 0.
Beta 0, exactly. So, okay, then the next one, x I 1, and then beta 1, right? Dot, 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 x I d, dot, 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 beta d. Okay. So what's nice about that is that this is exactly that beta vector that we defined. Actually, no, this is the first time we're defining it. I don't think we saw this before. We're going to give that a name as boldface beta. And we can see that this thing is similar, but not exactly the same as what we had in our feature matrix before. Because different from the feature matrix, this actually has this one additional column here, one additional entry 1. That wasn't there before. So what we're going to do now is we're going to define a new matrix called A that contains all of our data features, but it also contains a column of 1s as the first column. And that column of 1s is expressly there so that we can involve the beta 0 to get this prediction. Okay. And then we also have our vector of predicted quantities here. So I want to note that this is there now. Okay. All right, everybody with me so far? Okay, so how do I get this y hat? How do I express y hat in terms of the matrix quantities above? Exactly, it's the A matrix times that beta vector. Simple as that. So again, we now have like this kind of clean, easily interpretable thing happening. We have some matrix A that contains our feature data, and we have some vector beta, that contains designable coefficients. It's up to us to choose the beta. For the A, we don't have any choice. That's what we're given. So we pulled these things apart and put them in different buckets because they have very different roles. Okay, so this is what we have for training. Now, once we're done training, we've somehow come up with our beta coefficients, and now those are frozen. When we're applying this in practice, someone is going to give us a new feature vector, x, which we won't know the label. We won't know why, but they're going to give us x. How do we use our beta vector? How do we use our beta vector to get our y hat, which is our prediction of the true y, which we don't know? Any ideas? So I want to make some row vector here, and then I'm going to use my beta vector. The hint is it looks a lot like the rows of the A matrix. Okay, so we're going to put the beta vector here. That's now something we've designed. So what do I need to put in here? Exactly. We're going to have a 1 here, and then
X, the new values given.
okay, almost true. There's going to be an x here, but remember, x is a column vector. I need a transpose, exactly. So now I have like a horizontal concatenation between the scalar 1 and the d length row vector x transpose. Now that's a d plus 1 length
row vector, which works perfectly. I can multiply that times my d plus 1 length beta vector. Okay. Great. Is everybody with me in terms of the translating the problem into linear algebra speak? Okay, good. Yeah, so now we have a nice equation that we can use for training. And then we have a separate equation that we can use, I'll say maybe for application. In machine learning, that second thing is also called test often. Test or evaluation. You have this trained model, beta, now you're evaluating it with some new data where the features are X, this is your prediction, and you may or may not know the true target Y. So I'll write application or test. Good. Okay. Everybody good so far? We just have a couple more minutes, but we can talk a little bit about what we're going to do as a first step towards solving this problem. So this is what we've seen before. We have a vector beta, which contains all the designable parameters of our linear model. And this is how we use them to form a prediction. In particular, this is the prediction on the ith sample of our training data set. And as I mentioned before, we're going to take a least squares fit to the data. So what we mean by this is we have to define a fitting quantity, something we want to minimize, something that describes how much error we get. So we want to minimize that error. And so using the quantities we looked at earlier, we're going to take a sum across all our data samples of the difference between the true target yi and our predicted target y hat I. But now, because this is a least squares, we're going to square it. And this thing is going to be the residual epsilon on the ith data sample. So, in other words, what we're doing is we're looking at the prediction error squared, summed across all our data samples. And we're saying that that is called the residual sum of squares, RSS. And this is what we want to minimize. And if we minimize this, we're minimizing the sum squared error, and we're doing least squares. Is everybody good with all of that? Okay, let's try to visualize it. So what we have here is an example with d equals 2. Let's see. Do you want to do d equals 2? Yeah, let's do x1, which is going to be the first feature. x2 is the second feature. And this is our prediction, y hat. And you can see that it is, being a plane, it depends linearly on x1, meaning if I fix x2 and I increase x1, you can see that it increases with a fixed slope. Or if I fix x1 and I increase x2, you can see again a fixed slope in that direction. So the beta 1 is exactly the slope of this line, right? Because as x1 increases, this increases at a rate of beta 1. As x2 increases, this increases at a rate of beta 2. So beta 2 is the slope here. There's one more thing, beta 0. How does beta 0 affect that plane? It just shifts it up and down, right? So there's actually 3 adjustable parameters here, 3 degrees of freedom. If you just think about it, you have a plane. You can tilt it one way, you can tilt it another way, and you can shift it up and down.
So those are the 3 degrees of freedom. That's what we can control with our betas. And what we're given are those black dots. That's our data. And the epsilon, which is the error, so this is like for one of the i's, epsilon I is the height of that little red bar. So sometimes that error is positive, sometimes it's negative, but we care about the squared error, right? So it's positive or negative, it doesn't matter to us. Both of them are bad. We're trying to minimize that. So essentially, we're trying to move this plane around so that it sits in a spot that gives us the lowest sum squared error, the smallest sum of the squared lengths of all those little red lines. So that's what we're doing. Okay. Any questions on that? Okay, so we'll get into the math later, but that's the main idea. Have a good weekend. You guys, we'll see you back. See you on Wednesday of next week.